Hello everyone, my name is Nana and I'm from the Prati Academy. So today we'll see the last part of the chapter, that is structure of atoms. Okay, now we have seen the quantum mechanical model of the atom. In that we have also seen the hydrogen with respect to hydrogen atom and the Schrodinger equation. Then we have seen the orbitals and the quantum numbers. All these orbitals are arranged according to the quantum numbers. So there are four quantum numbers: principal quantum number, azimuthal quantum number, magnetic orbital quantum number, and the last one is the electron spin quantum number. So these are the four quantum numbers. Then we have seen the shape of the atomic orbital. So this is an s orbital. How will be a p orbital? It will be along the coordinates. Okay, and this is the d orbitals. Then we have seen their energy levels, that is ground state, excited state. Now the last part, that is the filling of the orbitals, how these orbitals are filled. Now the filling of electrons into the orbitals of different atoms takes place according to the Aufbau principle, which is based on Pauli's exclusion principle, the Hund's rule of maximum multiplicity, and relative energies of the orbital. These are the 4 points on the basis of which the electrons are filled in the orbitals. So we'll see all these 4 principles in this video. So that is an Aufbau principle, Pauli's exclusion principle, Hund's rule of maximum multiplicity, and relative energies of the orbitals. Now let's start with the Aufbau principle. Now what does an Aufbau principle means? The word Aufbau is the German meaning building up. Okay, Aufbau means building up, which is a German word. Now the building up of orbitals means the filling up of orbitals with electrons. Okay, building up means here it is the filling of orbitals with electrons. Now the principle states that in the ground state of the atom, the orbitals are filled in the order of their increasing energies. So from when they are in the ground state, means all the electrons are in their original energy levels. At that time, the orbitals are filled in order of their increasing energies, like from 1s, 2s, to p. So it will be filled in the increasing order of their energies. Orbital 1s, value of n is 1, value of l is 0. So value of n plus l is 1. So this you know. So 2p has lower energy than 3s. So 3p has lower energy than 4s. Okay, like this the energy levels are arranged. Now, in other words, electrons first occupy the lowest energy orbital available to them and enter into the higher energy orbitals only after the lower energy orbitals are filled. Now, in which order they are filled? So, first the orbitals, okay, orbitals with lower energy are filled. So electrons will first occupy all the orbitals which has the lower energy. Once these orbitals are filled, completely filled, then they will move to the orbitals with higher energy after they fill up all the lower energy orbitals. Now the order in which the energies of the orbitals increase, and hence the order in which the orbitals are filled is as follows. And this is the order how the energy of the orbitals are increasing, and in this order only the electrons are filled up, that is from 1s to 2s, 2p, 3s, 3p. After 3p you have 4s, then 3d, because 4s has relatively lower energy than 3d. That's why first it will be filling up the 4s and then it will go to 3d, because 3d has more energy than 4s. So as the principle says, first the lowest energy orbitals are filled, then they go to higher energy orbitals, right? So therefore 4s is filled first and then they will go to 3d, then 4p, 5s. After 5s will be your 4d, because 4d is higher in energy. Then 5p and 4f. 4f comes after 5p, because 4f has higher energy than 5p. So in this order is the electrons are filled in an orbit. Now the order may be remembered by using a method given here. So this order of filling, there is a method given here. I'll show you. Starting from the top, the direction of the arrows gives the order of filling orbitals. That is starting from the top right to the bottom left. Now this is how it is filled. So the arrow indicates the filling up of the electrons. So it starts from 1s, it goes to 2s, then it goes to 2p, 3s, then 3p, 4s, 3d, 4p, 5s, and so on. So this is the order how it is filled. Okay. This is the Aufbau principle. The next is your Pauli's exclusion principle. The number of electrons to be filled in various orbitals is restricted by the exclusion principle. Now, once you know the order of filling of electrons, now you want to know? You want to know how many electrons are to be added in one orbital, right? You can't add as many as you want, right? So there should be a fixed number of electrons that should be added into one orbital. Now, that is what is given by the exclusion principle, or that is decided by the exclusion principle. Now, it was given by an Austrian scientist, Wolfgang Pauli. That's why it is Pauli's exclusion principle. Okay. According to this principle, no two electrons in an atom can have the same set of four quantum numbers. Or simply, you can say only two electrons may exist in same orbital. Okay. In one orbital, you can have two electrons coexisting with each other only at one condition, that both the electrons should have a opposite spin. Okay, if this is spinning like this, then this should spin in an opposite direction. In this direction should spin, and its spin should be in this direction. So one should have a clockwise spin, and the other one should have an anti-clockwise spin. So Pauli's exclusion states that only two electrons may exist in the same orbital, and these electrons must have a opposite spin. This means that the two electrons can have the same value of three quantum numbers, that is n, l and m, that is principal, azimuthal and magnetic quantum numbers. They should have all these three values same, but they must have a opposite spin quantum number. Okay, that means one should have a plus half and one should have a minus half spin, because spin quantum number is given by plus half and minus half, right? So one electron should have a value of plus half and the second electron should have a value of minus half. Okay, so the restriction imposed by Pauli's exclusion principle on the number of electrons in an orbital helps in calculating the capacity of electrons to be present in any shell. So this exclusion principle helps you to calculate the capacity, like how many electrons will be able to put into a subshell, or how many electrons can a subshell take. This capacity can be calculated by using Pauli's exclusion principle. For example, subshell 1s. Okay, 1s comprises of one orbital, and thus the maximum number of electrons present in 1s shell can be 2. In p and d subshells, the maximum number of electrons can be 6 and 10. Right? S, P and D. S can take 2 electrons, whereas P can take 6 electrons, 2 in each columns, right? So you can have 6 electrons. D has 5 columns. So 5 columns, 2 with each, you can get total 10 electrons in D, 6 electrons in P and 2 electrons in S, and so on. So this can be summed up by the maximum number of electrons in the shell with principal quantum number n is equal to 2n square. So by using this formula, you can calculate how many electrons you can add in each subshells, and that calculated values are for S it will be 2, for P it will be 6, and for D it will be 10. Okay, now that is what Pauli's exclusion principle states. So above principles allow you to, or it tells you about the arrangement of the orbitals, which is the first orbital, which is the second orbital, in which what is the arrangement, like 1s, 2s, 2p, according, and this is done on the basis of their energy level. So how the orbitals are arranged, in which pattern the electrons will be added into the orbitals. So this is what given by the above principle. Then Pauli's exclusion principle tells you about the number of electrons that can be added into each of these subshells. Okay, that is what your Pauli's exclusion principle states. Now, next is your Hund's rule. Now, what does Hund's rule of maximum multiplicity states? So, this rule deals with the filling of electrons into the orbitals belonging to the same subshell. That is, orbitals of equal energy called degenerate orbitals. Okay. Now, this rule deals with the filling of electrons into the orbitals belonging to the same subshell. Okay. It states pairing of electron in the orbitals belonging to the same subshell, that is P, D or F, does not take place until each orbital belonging to that subshell has got one electron each, that is, it is singly occupied. So for P, D and F, there are subshells. Now, Hund's rule of maximum multiplicity, it states that pairing of electrons. Okay. Now, for example, this is P. P has three subshells, right? One, that is Px, Py and Pz. Okay, you have three subshells in P. Now the pairing of electrons in the orbitals belonging to the same subshell does not take place until each orbital belonging to that subshell has got one electron each, that is singly occupied. Now how the electrons are filled in these three subshells? If I have one electron here, okay, I have one electron here, the second electron which is coming, it won't be directly go and pair with this electron. Okay, for pairing to occur, you require these orbitals to be filled with single electrons first. When all these three orbitals are filled singly, after that whatever electron comes next will be the one which will be used to pair them. Got it? So Hund's rule of maximum multiplicity states what? You will have pairing of electron in these subshells only when all the subshells had single electrons occupied first. When all these orbitals have one single electrons occupied initially. Now for p orbitals you have three subshells. So for three subshells you can add 6 electrons, right? So first 3 electrons will be occupied singly unless and until it is occupied singly in all the 3 orbitals, the other 3 electrons won't be added. So for pairing to occur in these subshells, it should already be filled with single electrons first. So all these 3 orbitals should be filled first with one electron. After that only you can add the another electrons. Okay, directly like this pairing of electrons doesn't occur with the two empty subshells. Okay, this is what Hund's rules say. Ki this type of filling of subshells doesn't occur. Subshells are filled only when all the three subshells are initially should be filled with one electrons, and then it is paired with the other electrons which are remaining. Okay, this is what Hund's rule say, that the pairing of electrons in the orbitals belonging to the same subshell does not take place until each orbital belonging to that subshell has got one electron each, that is, it is singly occupied. Okay, since there are 3p, 5d and 7f orbitals, Therefore, the pairing of electrons will start in the p, d, f orbitals with the entry of 4th, 6th and 8th electron. Now, what do you mean 4th, 6th and 8th electron? So, with respect to p, if I tell you, so this is 1, 2, 3. Now, the next electron I'm going to add will be the 4th electron. So, the pairing will start with the 4th electron. Similar for d orbitals. D orbitals have 5 subshells, right? So 5 subshells, 1, 2, 3, 1, 2, 3, 4, 5. 5 electrons are added already. Now the sixth one will start with the pairing. 6, 7, 8, 9 and 10. So sixth one is the one which will start with the pairing. So that is 6. Now for f orbitals you have 7 subshells. So first each of the 7 subshells will be filled with 1 electron and the 8th electron will start with the pairing. Okay, this is how it is pairing and this is what your Hund's rule of maximum multiplicity states. Okay, now it has been observed that half-filled and fully filled degenerate set of orbitals acquire extra stability due to their symmetry. So when the shells, okay, when the subshells 1, 2, 3, 5 and 6. Now this is a p shells, right? P orbital. This p orbital is half filled. Half filled means all the subshells has 1 electrons in it. So this is a half filled orbital. Here it has all the 6 electrons. So this is a full or completely filled orbital. Okay. Now this half filled state or completely filled state gives this orbital an extra stability. And this stability is due to their symmetry. Okay. So whenever any molecule, any element has a half filled or completely filled p, d and f orbitals, that molecules are stable in their state. Okay. Now, next is the electronic configuration. Now how you will apply this shell or rules, where you will apply. So you will mostly apply these rules in the electronic configuration. So an atom, it is represented by an electronic configuration. So the distribution of electrons into orbitals of an atom is called electronic configuration. So all this now you have seen the orbitals, how the electrons are added into the orbitals, what are the orbitals. Now this distribution of electrons into the orbitals is known as electronic configuration. Okay, if one keeps in mind the basic rules which govern the filling of different atomic orbitals, the electronic configurations of different atoms can be written very easily. Okay. So if you remember all these rules and the properties, you can easily write the electronic configuration. The electronic configuration of different atoms can be represented in two ways. For example, this is one way how you can represent an electronic configuration, that is SAPBTC notations. And next is the orbital diagrams. It's an orbital diagram. Okay. I'll show you both the notations. So in first notation, the subshells is represented by the respective letter symbol and the number of electrons present in the subshells is depicted as the superscript like A, B, C. Okay. Now here what happens? Now for example, if I take lithium. Okay. Lithium has an atomic number of 3. Okay. So if I notate it in the first SPD notation format, then it will be 1s2, 2s1. So this is how you notate the lithium in first format. Now if I want to notate it in second format, that is orbital diagram format, then S has one box, right? So 1, 2 and here it is 3. So this is the orbital diagram notation. Okay, so similarly, the subshell represented from different shells is differentiated by writing the principal quantum number before the respective subshells. So in the second notation, each orbital of the subshell is represented by a box and electron is represented by an arrow. Okay, a positive spin. So this is a positive spin and this is a negative spin, or this is the plus half, this is the negative half. Okay, so the advantage of second notation over the first is that it represents all four quantum numbers. Okay, so first one, that is 1s2, 2s2, 2p6, this doesn't give you anything with, this doesn't represent all the four ones. Here you can get only the principal quantum number and the azimuthal quantum number. But the second one, where you represent it in a box format, okay, orbital diagram format, the advantage of this notation over this notation is it represents the all four quantum numbers. Okay, now the hydrogen atom has only one electron which goes in the orbital with the lowest energy, namely the 1s. Since hydrogen has only one electron, it will go in this diagram, 1s shell. Okay, and the electronic configuration of hydrogen atom is 1s1, meaning that it has one electron in the 1s orbital. Okay, if you write it 1s1, that means you have one electron in 1s orbital. Now for helium it will be 1s2 because helium has two electrons in 1s orbitals. Okay, second electron is helium, can occupy 1s orbital. Okay, its configuration is 1s2. So as mentioned above, the electrons differ from each other with opposite spin, as can be seen from the orbital diagram. So 1s1, the arrow will be a positive arrow, and in helium, since there are two electrons, one will be positive, one will be negative. This is what Hund's rule, this is what Hund's rule had said. And along Hund, not only Hund's rule, Pauli's exclusion principle also says the same thing. Okay, Pauli's exclusion principle is the one which says ki an orbit can have two electron only when they are in opposite spin. So this is what they mean by opposite spin. Okay, these are the electronic configurations of other atoms. Okay, now the electronic configuration of elements sodium to argon follow the exactly same pattern as the elements from lithium to neon. So all of them follow the same pattern. Okay, all of them are filled along the same pattern. From lithium to neon, with the difference that the 3s and 3p orbitals are getting filled now. So as you increase the atomic number, you will be increasing the shells because the electrons will go on increasing, right? So you will keep on adding the electrons, keep on adding the shells so that you can add all those electrons. So this process can be simplified if we represent the total number of electrons in the first two shells by the same of element neon. The electronic configuration of the element from sodium to argon can be written as sodium Ne3s1. Now, instead of writing the entire table like this, okay, what you can do is the electronic configuration for neon. Neon is 1s2, 2s2, 2p6, right? This is neon ka electronic configuration, that is 1s2, 2s2, 2p6. Okay, this is the electronic configuration of neon. If you see this configuration of sodium, sodium ko configuration is 1s2, 2s2, 2p6 and 3s1. This part and this part of neon is same. So for simplification, instead of writing this entire table, what you can do is for this part, you can add Ne in a bracket, then 3s1, which means ki before 3s1, okay, sodium has a configuration similar to Na. So this will reduce the big lengthy electronic configuration. So sodium ka configuration you can write it as Ne3s1 to argon. So sodium till argon you can use Ne because here you will be filling all the 3s and 3p orbitals. So this will remain same for all the molecules starting from sodium till argon. So from sodium to argon, you can use any in front of their electronic configurations. So the electrons in the completely filled shells are known as core electrons, and the electrons that are added to the electronic shell with the highest principal quantum numbers are called valence electrons. Now, the electrons which are added to this, okay, for example, if I'm taking sodium, okay, so this neon ka part, electronic configuration, okay, so these are completely filled, right? S orbital is also completely filled, this also completely filled, this 2p is also completely filled. So this part where all the orbitals are completely filled with respect to sodium, okay, this part is known as core electrons, okay. This part is known as core electrons, where all the shells are completely filled. And this 3s orbital with higher energy level and is starting to filling up, okay, with the highest principal quantum number. Okay, compared to them, this is the highest principal quantum number, right? So this is a valence electron. Got it? So this completely filled group, this is known as core electrons. So I'm telling you with respect to sodium, but this is same for all atoms, okay? So this is the core electrons where all the subshells are completely filled, and this part is the valence electron with the highest principal quantum number, okay? Now, for example, the electrons in neon are the core electrons, and the electrons from sodium to argon are the valence electrons. Okay, so in potassium and calcium, the 4s orbitals being lower in energy and 3d orbitals is occupied by 1 and 2 electrons respectively. Now, this is where we will start with the d orbitals. Okay, a new pattern is followed beginning with the scandium. Okay, scandium being the lower in energy, then the 4p orbitals is filled first. Consequently, the next 10 elements. Okay, now scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. These are zinc. These are the d orbitals. Okay, 5 3d orbitals are progressively occupied. Okay, these elements starting from here, all the electrons will start adding up in the 3d orbitals. Okay, there also is exception with chromium and copper. Okay, now what is the importance of knowing the electronic configuration? Now I know how to add the electrons and how to write it in an electronic configuration format. Now, what is the use? So the modern approach to the chemistry in fact depends almost entirely on electronic distribution to understand and explain the chemical behavior. So most of them, they depend on the electronic configuration, electronic distribution to understand the chemical behavior of the atom or the molecule. Now, for example, questions like why two or more atoms combine to form molecules, why some elements are metals, why others are non-metals. Okay, all these questions, why helium and argons are not reactive, but elements like halogens are reactive. So all those things, how atoms form a molecule, how atoms are combining with each other. So these are the things which can be explained using the electronic configuration part. Now, stability of completely filled and half-filled subshells. Ground state electronic configuration of the atom of an element always corresponds to the state of the lowest total electronic energy. Okay, so the ground state means the energy is low. Is it lowest total electronic energy? Now, the electronic configuration of most of the atoms follow the basics rule, right? Rules like the Aufbau principle, Pauli's exclusion principle, Hund's rule. Okay, they follow these basic rules. However, in certain elements like copper and chromium, where the two subshells 4s and 3d differ slightly in their energies, an electron shift from subshell of lower energy to a subshell of higher energy, provided such a shift results in all orbitals of the subshell of higher energy getting either completely filled or half filled. Now this part, stability of completely filled and half filled orbitals. Now, copper, copper and chromium, okay? Both of them have an electronic configuration where first, these are transition elements or 3D elements, where 3D orbitals are filled, okay? For example, you can see here. So these are the orbitals, okay? Now here is the chromium and this is the copper, okay? Chromium is 24 and copper is 29. You can see this is the 3D orbital and this is the 4s orbital. Now here for chromium, it is 3d5 and 4s 1. Okay, and for copper it is 3d10 and 4s 1. Whereas all the other molecules have two 4s electrons. So the trend for 3D orbitals to be filled in a transition series, okay, is like this. So from scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. Okay, so this is the 3D series. So these electrons are filled like 3d0 4s1 because it is 21. So the atomic number is 21, 22, 23, 24, 25, 26, 27, 28, 29, and 30. These are the atomic number. Now the electrons are filled in the manner ND 1 to 10, not 0 to 10, and 4s 1 to 2. Okay, this is the general pattern. Okay, ns 1 to 2, nd 0 to 10, ns 1 to 2. So here it is 3D series. So I'm taking 3D. 3D orbitals are filled in this series. Okay, these atoms. So 3d0 4s1, 3d1 4s2. Okay, 3d2, not 3d0. It is for scandium. Okay, for scandium, it is 3d1 4s2, 3d2 4s2, 3d3 4s2, 3d5 4s1, 3d5 4s2, 3d6 4s2, 3d7 4s2, 3d8 4s2, 3d10 4s1, again 3d10 4s2. As you see the electronic configuration of all these molecules, except for chromium and copper, they follow a same trend, right? They all have 4s2 in their 4s shells, right? Two electrons in their 4s shells, except for chromium and copper, which has 4s1. Now, why they show this different electronic configuration? Why don't they follow the trend? Okay, if they follow the trend, the electronic configuration should be 3D, 4 and 4s2. And here it should be 3D, 9 and 4s2. This should be their actual electronic configuration, right? If they would have followed this trend, but they show a configuration of 3D5, 4s1. This is because the 4s subshell has relatively lower energy than 3D. That's why 4s is filled first and whatever is remaining is added to the 3D shell. Now, in chromium and copper, if they had followed this pattern, okay, then it will be they require only 1 electrons, 3D 4 and 3D 9. They require only one electron to make it a half filled or a completely filled orbitals, right? They require one electron to make it a half filled or completely filled. So for that reason, what they do is they take one electron from this 4s orbital, okay, and they add that one electron to the 3D orbitals. And by doing this, what they make is they make a half-filled d orbital and a completely filled d orbital, which gives them an extra stability. So all these atoms, they require a stable condition, right? So chromium and copper, to make themselves stable, they take one electron from the 4s orbitals. Okay. So that's why there is a difference in their electronic configuration. Okay. So chromium and copper were two subshells. 4s and 3d differ slightly in their energies. An electron shift from subshell of lower energy, that is 4s, to a subshell of higher energy, that is 3d, provided such a shift results in all orbitals of a subshell of higher energy getting either completely filled, for example in chromium, in copper, it gets 3D 10, right? So copper, it gets completely filled, and chromium, it gets half filled. Okay. The valence electronic configuration of Cr and Cu therefore are 3D5 4s1, 3D10 4s1 respectively, and not 3D4 4s2 and 3D9 4s2. So instead of this electronic configuration, they have this electronic configuration. Okay, it has been found that there is extra stability associated with this electronic configuration. So this is the last part of the chapter. Okay, I hope you all have understood what this chapter basically is. It's about all the atomic structures regarding the structure of atoms. What are the structure of atom and what is the one which we use, which we now you using is the quantum mechanical model. It is the one which we use now. And this quantum mechanical model, how those electrons are made, how those orbitals are filled up, okay, how to represent them, all these things are given in this chapter. So thank you for watching my video. Please do like, share and subscribe to our channel.